Hello. My name is Amjad, and I'm recording this as the videos weren't working in the class. So this is to present my homework one. Um, as we all know that we would be just playing with varying the currents to see the action potentials as the voltages for the Hodgkin-Huxley model that we have. So the homework had three parts. The first one was DC current, and then we had a sinusoidal current and then pulse current. So I'll be going over those. So as DC current has just one variable, so I would be changing current. So I made this in a video so as to be able to better visualize it for everybody because all the graphs are sequential. So I increase current little by little, so the graphs progressively move forward. So I thought video was a good idea. So here it is. I just start the video. It would start from zero current to a very little current, and then it'll keep going on. So as we apply a very small current, there's a very small voltage spike, but till the time it hasn't reached the threshold, we don't see an action potential. But when it does, right here, so till 0.021 milliamps, we see the voltage is there. It's tiny-ish, but not there yet. And at 0.023 milliamps, still no spike, but the voltage is rising. And as we get to 0.024, we see that there's a spike. So it increases little by little, but as soon as it gets to the threshold, it spikes and we get a single spike. And as we keep increasing the current, so we see the second peak coming up and then it spikes too. And increasing the current further, we see a third one, and then we see a bunch of those. They're coming up. So yeah, right there. So it'll keep happening as we increase the current more and more. We see more and more spikes till eventually we get to a point where we have our entire screen full of spikes, and then increasing the current further. We increase the frequency of the spikes, so they are occurring more rapidly. And if you've noticed the time scale, I have half a second time scale at the bottom. It's 500 milliseconds. So the frequency of the spikes is really easy to calculate. I also just computed the total number of spikes so that we don't have to count 1, 2, 3, 4 for so many spikes. So right now at zero point 0.2 milliamps, we have about 44 spikes. So 44 spikes in half a second. So it's like 88 spikes in one full second. So we can say it's like 88 spikes per second, or we can say the frequency of spike is 88. Um, just for the fun of it. So yeah, this is the evolution of the spikes when I vary the DC current from 0 to zero point 0.2 milliamps. So that was the first part of the homework. Moving on, sorry. I also included this code in the slides. It's just a tiny routine to record these videos. It was just to automate the process. So I made vector of like the DC currents I wanted to use, and I just initiated a video object. The Hodgkin-Huxley model that we had, I uh, tweaked it a little bit. I made it into a function so that I can pass current into it and get the voltage out. I got the T out as well for graphing purposes. So this one in the middle at line 10 is basically my call to that function. I get the voltage, I just plot that, I capture the frame, I put it in the video, I capture the next frame. So that's just how I did the video thing. So I think I would be able to maybe upload a folder with all this codes and all these videos, so that if anybody wants to experiment with something, so it would be available. So moving on to part two of the assignment, now I'm going to play around with AC currents. So when I have sinusoidal currents, there are two components. So we have the magnitude of the DC current, the magnitude of the current, but as well as the frequency. So uh, there are two variables. So in a graph and like evolving graph, I cannot if I can change two variables simultaneously, but then it wouldn't make too much sense. So what I did is I made several graphs for various different frequencies while varying the amplitude little by little. So the first graph right here is for a frequency of 5 hertz, and so I would vary the amplitude uh, starting from 0 to a very little value, and uh, we'll see how that goes. So when I have a very small amplitude of the current at 5 hertz, we see that this is the current graph, and I've already mentioned in here that the plot of current is not to the scale. So you see the y-axis, it's voltage in millivolts. It starts from -80, it goes all the way up to 60 millivolts. So this is voltage, but the current is just for reference. I haven't put a y-axis for that. It's just to see the shape and where the peaks are so that we can relate to stuff. For example, if you see that as the amplitude has increased to 0.09 uh, milliamps with a 5 hertz frequency of the sine wave, we can see that the voltage is started to increase at certain regions where the peaks are, and we see that the same things, that the voltage is rising to a certain point, and it's just getting closer and closer to threshold, and maybe in the next frame when I play the video, it would just shoot up to give us the spike that we are so used to see, and then increasing the amplitude further, we see 2 spikes and 3 spikes, and so this is what goes on with increasing the amplitude, or while I have the same frequency of 5 hertz. So we see that there are a bunch of spikes, then there's nothing, then bunch of spikes again, then nothing, and this repeats. And this is very easily explainable when I have the graph of current with it, and we see that whenever there's a peak, we see all those spikes. So this takes a little bit of mystery out of why they spike in bunches, but that is one phenomenon that is very easily explainable. Uh, they have other mechanisms when they fire in bunch and then they don't, and then they fire in bunch. We'll get to those later when we are at pretty higher frequencies. So that is kind of unexplained, you can say, but this is too obvious. So there's nothing too spooky here, that why we have a bunch and then no firing and then we have a bunch. It's pretty obvious, especially when I draw the current right on the same graph, and you can see that this is actually 5 hertz because this is half a second. So um, we see 3 peaks in half a second. So if it was a full second, you would see 5 peaks. So that would be like 5 hertz frequency. So that's how I know that this is a 5 hertz and not 5 kilohertz or something. So yeah, the comment I was making earlier in the class. So because I can see and I can count the peaks, and I actually made this graph 1 second long earlier, but then things become too tiny. So I just thought that a better way to present this would be to limit my x-axis to half a second, and we can simply multiply anything by 2 to get the frequency of that thing. So moving on, I increased the frequency to 10 hertz, and we can see that similar things happen. So as the amplitude of current is increasing, the voltage starts showing those uh, things that are rising a little bit, and they're as they rise just a little bit more and they touch that threshold level, all of a sudden they would just spike. So that's what happened at that particular amplitude, and then increasing the amplitude more and more, we see multiple spikes. When the voltage is high and when the current is high, and when the current goes to its dip, then we don't see any spikes. And uh, when we come to the next bump, we see multiple spikes again. So that's at 10 hertz. Going forward to 20 hertz, it's similar, but we would see some new stuff, and I would keep pointing to stuff. So if you are also noticing the amplitude at which the spiking begins, so you see as we are increasing the frequency, um, spiking starts happening at lower and lower amplitude. So initially it was happening at about zero point 0.9, then it for 5 hertz, then it came down to about zero point 0.6 or something, and now we see the spikes happening for 20 hertz at only about 0.03 amplitude value. And we see one spike there, the other one is trying to come up, and as we increase and increase the amplitude, we see the other spike. So another thing that is pretty obvious is that the width of the peak of the current, the sinusoidal current, is thinning out. There's not enough space in time on those peaks, because they're getting narrower and narrower, and so there's only enough room to accommodate just 2 spikes on a single a hump. So we have one spike, and then neurons have the refractory period, and then they can they have to wait a certain time before they can fire again. So they have that time, then they fire again, and by the time they return, so the peak is already gone, and then there's dip, so they can fire twice, and then they would fire again on the next cycle. So that's what happens at 20 hertz. So moving on to 30 hertz, we see that um, some interesting things starts to happen, and that's what I was referring to. So all these peaks are the same. The current waveform, if you see at the bottom, one of the things to note here is that at 30 hertz, it starts spiking at even lower amplitude, 0.02 something. So that is pretty small. And also you see some what you might say as anomalous behavior, like there are 2 spikes, then there is silence for about 2 spikes. They're trying to get to the threshold voltage, but not quite. So there are no spikes for the next 2 peaks. Then there are 2 further spikes, and then the voltage is trying to get to the threshold, but isn't able to. So we don't see any further spikes. Moving on, we have four spikes and then none. Then moving on, we have four spikes, then six uh, peaks without any spikes. Then we have the next two spikes on the next two peaks. Then we have missing. So this is like bunch of firing, then a silence period, then a bunch of firing, and this is kind of unexplained. So in the initial sites at just 5 hertz or 10 hertz, it was very, very obvious. Like you would see that there are five spikes, then there's a silence, then there are five spikes, and that corresponded with the peaks in the uh, current. So that was pretty obvious. But this thing is not so obvious. So we see four spikes and there are none, then again two spikes, then none. So this is how it's going. And as I play the video, it would continue for this entire thing. So these come closer and closer, then they become four, so then they become six, and then there's a gap, then there are some more. So and if you also notice, I'm changing the amplitude very, very little. So it's not like this thing keeps happening and these things are dancing around. It's just that this sweet spot of the amplitude at which this anomalous behavior is happening. If I was increasing like incrementally from 0.01, 0.02, 0.03, I wouldn't even see this dancing around of these spikes. But as I'm increasing the amplitude very little by little, so I'm able to see, okay, a bunch here, a bunch there, gap in between, then a bunch appears. And this happens even beyond 1 second. So when I was playing around with it, I had this graph all the way beyond 1 second, and I could see that this was going on. It's not that it disappears after a certain time. So it goes on pretty much. So after a while, when we get to about zero point 0.3 in the amplitude, then we see, okay, about one spike per a peak in the current. So that's kind of very obvious. And we can see the number of spikes is 15, and the frequency, as I already told you, that my x-axis is half a second. So if you multiply just 15 by 2, or maybe divide 15 by 0.5, 15 divided by half is like 30. So we get 30 spikes for 30 hertz frequency. So it's like one on one. So starting at an amplitude of about 0.3, you get the spike frequency equal to the applied signal frequency. And this would remain that way for a very large window of the amplitude, starting from 0.3 all the way till about 0.18. We have one spike per peak, but going beyond that, we see that the other spike is also coming up. So that would also fire. So we would again get to, oh, we did not get that. But if I increase the amplitude a little further, we would get two spikes on this. But that said, moving on, so we have 40 hertz. Again, we would see some very similar things. So there are a few spikes and jumping here and there. Here, if you notice, it was a little different that there were a null period in the beginning, then we had a lot of spikes. If I had it beyond this half a second, it would be some spikes, then some missing thing, then spikes, similar to what we saw for 30 hertz. And again, if you have noticed, spiking started at 0.01 something. So as we're increasing the frequency, this spiking is happening at a lower and lower amplitude. So initially we needed 0.09, then we needed 0.06, then around 0.03 or something, and now it's come down to 0.01 to see a spike train. And if we keep going forward, so we have the same spikes going on, and then it's pretty much stable, one spike per peak of the sinusoidal current, and that's what happens. So we move on to 50 hertz. And for 50 hertz, again, we see stuff like that. Only two spikes come up at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So on 13th peak and 14, 15, 16, 17, 18. On 13th and 18th peak, we see one spike and then another spike and then again some silence, and it happens at amplitude of only 0.015. Going just a little further, we see almost equally spaced. So we have one spike, some no spikes, then one spike, then again some time with no spikes, and this happens, then they become a little asymmetrical. We have two that are a bit closer together, then we have a little wider difference, then we have two. These are the behaviors that we were saying, oh, there were a bunch of spikes and then they are not. And but this only happens at the at the onset. So if you notice the amplitude, I change it very minutely, and at that time I see all these effects. If I go incrementally from 0.01 to 0.202 to 0.03, I would miss those things mostly. So it isn't like it's going on over a wide range. I have expanded it by including these minute amplitude changes. But other than that, you would see no spikes, then you would see spikes, and you would move on without noticing it. But at the time when the spikes start, these randomish behaviors occur. But from 0.17 onwards, like it would be pretty regular thing. So and at point 4, it becomes just one spike per peak, and then it would stay like that till the amplitude at which I go about point 2. So that's what happens at 50 hertz. So when we get to 100 hertz, things are again not too different, but one of the very first things that you notice that we have already reached an amplitude of 0.02 and there are no spikes. So we keep going forward, and at 0.023, so uh, initially the effect was that for 5 hertz, a higher amplitude started the spiking behavior. Then we had lower and lower amplitudes uh, producing spikes, but now again it's starting to rise. So the last one was starting at 0.015, but for 100 hertz it's 0.023. So a little higher amplitude got the spikes going, and we don't have one spike per peak in the current because the neurons don't have enough time to settle and fire again. So they fire at one of the current peaks, then they try to, but they aren't quite able to fire on the second peak. And then when the next current peak occurs, then they're able to fire again, then they would miss a peak, and then they would fire at another peak. So the frequency of the current is 100 hertz, but if you see the number of spikes is 25, so dividing by half a second, we have 50 spikes per second. So we are missing every other peak. And if we keep on increasing the amplitude, I think we would be able to get those spikes to not quite. So we get 2 spikes, then we miss one, then we get 2 spikes, then we miss one, and now we get 4 and miss one. And but increasing the amplitude continuously, we get to the point where we have one spike per peak. So this is for 400 hertz. And for 200 hertz, we see that um, things are starting similar to before, but you see the amplitude is increasing and we don't see any spikes yet at 0.04 and 0.05. So the spiking is kind of starting to delay with the amplitude. So it was happening at a much lower amplitude before this point, but now it's 0.07 and we see just our first spike, and then at 0.08 we see a bunch of more spikes, and then at about zero point 0.1 we see the spike train, and then it would um, move on, like in the case of 100 hertz, like we have some spikes and then we have more spikes and stuff like that. So this time I increased the amplitude till zero point 0.3, but I'm not a big fan of increasing the amplitude beyond a certain limit. And the reason is not so obvious in the graph, because the negative side of this graph goes as low as minus 140, and that wouldn't be characteristic of a neuron. So I think of this as I'm breaking the model. So this is a mathematical model trying to model an actual neuron. So a neuron's behavior is in a certain range, but if I go beyond that range, I increase the amplitude by a lot, unrealistic for a neuron, or I do some other stuff. So because it's a mathematical model, I would see some graph, but that wouldn't be representative of a neuron. So uh, increasing an amplitude beyond a reasonable limit, and by reasonable limit, I see if the voltage is going far too down to be consistent with what we know about neuron, is like not a value to use. So, but for the simulations, I would use a few values anyway just to show, but increasing beyond this wouldn't make too much sense, because that wouldn't be representing a neuron. It's just the model would start to deviate from the actual neuron at that point. So so moving on to 300 hertz, we see that similarly, higher, even further higher amplitude would trigger the spikes. So it's in about zero point zero 0.02 range, and we don't see any spikes. It would be like zero point 0.8 or zero point 0.9 at which, yeah. So at 0.09 we see the first spike, and at about 0.14 we see the spike train, and then increasing it further and further we see more and more spikes. So uh, similar behavior, and again I increase the current to zero point 0.3. So now we move on to 400, and it would be a similar story again. A very higher amplitude compared to the previous examples would trigger the spike. And but at this point, I got rid of the current wave, because it's not adding any information. It's just blocking the bottom part, because the frequency is so high that it's just filling up the space, and we aren't even able to see the peaks. So I just got rid of that, and yeah, you can just see that it's a higher frequency and we are just increasing the amplitude, and there's something happening, but uh, the voltages aren't rising enough. Also, at 0.13, the first spike was able to go off, and then we see that increasing it at to a value of zero point 0.2, we see uh, the spike train, and then 0.25 we see that, then I increase it from 0.3, zero point 0.4. So this is how it goes for 400 hertz. Now we go to our 500 hertz, and well, it would be kind of similar stuff. So again, I don't have that current thing. I got rid of that, and we are increasing the amplitude, and at about zero point 0.1 we would see first spike, and even beyond that we would start seeing the spike train. It would just come on any minute. So it's about here now. So we see it right now. So we see the spike train at about zero point 0.3. So there we go. We have our familiar spike train, and things are going good. Moving on, we have 700 hertz, and at this time it would be like very high values of amplitude would result in a spike, and they might be at the verge of being realistic, and that's why not at 700 but at 1 kilohertz I thought, yeah, that is the limit. But because at 700 you're still able to get a spike train at about 0.3, 0.4, and the this voltage is not going too much in the negative. It's still touching minus 80, but not going like at minus 160 or something. So that's what happens at that. So this is a full kilohertz or 1,000 hertz. So at this point, you see that it would start spiking at zero point 0.3, and then we get the spike train at a unrealistic like point where 0.85. So that's too high. So I would say that although I would still able to get those spikes by increasing the amplitude by a lot, which I think is unreasonable, but I just did it for the simulation. But yeah, I would say that at this point, this is no longer spiking for the amplitudes that it was spiking before. And um, I haven't included the graph for 1500 hertz or 1.5 kilohertz, but at that point, I would see a spike that is coming down, and before getting all the way below minus 140 or minus 60, it would spike midway. So it would be a peak. The peak is declining, and then it reaches some 20 millivolts, or before touching even zero, it would just start to rise again. So it would be a double spike. So that is not what Neuron does. So it's just an artifact of the model, because it's using the model outside of its working domain. So that wasn't very characteristic. So I haven't included it here. I just included till 1,000 hertz. And you still see that at 1,000 hertz also, to get this spike trend, we had to increase the uh, this by a very large value. So that is like the limit of it. It was one of the questions in the homework as well, so that's why I've addressed this. And moving on to the third part, now we were dealing with pulse, and for the pulse we have three parameters. So for the first part, it was just DC, so it was just a single component. So it was like just one value of current, so I could change it, and I had just a single evolving graph. For the case of a sinusoidal current, I had two things, the frequency of sinusoid and amplitude of sinusoid. So that's why I had several graphs, fixing the frequency and changing the amplitude in every graph. Now I have three variables. So if I fix one and keep changing two, it would take a lot of graphs to show that. So I fixed the amplitude based on the part one that was suggested in the homework as well, that my first spike that I received on my DC current was at about 0.023, or 23 was at the word, so I received my first spike at 0.024, so I could have used any value, but I used this value and I fixed the amplitude. I also fixed the duty cycle at 50%, so I can lower it and I can increase it, and it would change stuff, but I just kept the duty cycle in the middle at 50%. I just kept it there, and I only changed the frequency, so as to not overwhelm by too many graphs. So it's just the square pulse at the bottom that would be changing only in frequency. So here we go. So as we increase the frequency, we have more and more spikes that are corresponding to the frequencies. But you notice, so till 25 hertz, we see one spike per pulse. But as we go to 30 hertz, we kind of miss the threshold by just a little bit, so we don't see any spikes. But moving on, at 35, we see two spikes, then we miss a spike, then we see two spikes, then miss a spike. It's a pattern like that. Going on at 40 hertz, it spikes for every single one of them. 45 still the same, and at 55 we again start missing one spike after every two spikes. So then we make it regular, like a spike once, miss two, spikes once, miss two, and that makes sense from the earlier sinusoidal excitation as well, because there isn't enough time to spike multiple times in a single in a short time. So it would spike, and then because of its refractory period, it would miss a few, and then it would spike once. So that's the behavior we see here. And moving on, 75, and at 80 hertz, we miss it completely. And again, it's a similar thing we notice in the sinusoidal current, that at very higher frequencies, you needed higher amplitude to spike. So I'm keeping the amplitude fixed. So when I increase the frequency beyond 80, there are no further spiking. So 80, 85, 90, 95, 100, but there aren't any spikes, and I can make it spike if I increase the amplitude, and that's what I saw in the sinusoidal current case, that for as I was increasing the frequency, it was becoming easier and easier to spike by I mean by putting less and less amplitude of current, it would spike, but beyond a certain level, like when I got to the 100 hertz point, then more amplitude would be required to make it spike, and that's what is happening here. But because I'm keeping the amplitude fixed, so I wouldn't see any spikes beyond this point, and I'm not making a lot of graphs for this thing, so it's just one graph, but because of the previous sinusoidal graph, we get the feel of where things are going. So that's what has happened here, and but I think that's pretty much it. So yeah, that was the last slide. So that's it. Thank you.